So let's continue with our discussion of sorting and look at another simple sorting algorithm. So as we said before, there are many motivations for sorting, starting from searching to removing duplicates to computing some statistical properties such as frequency tables and so on. And the example that we have in hand is one where we are asked to sort a bunch of exam papers in descending order of marks. So a second strategy to sort this bunch of exam papers would be the following. So you take the topmost paper in this stack that you have and create a new stack with that. Now you take the second paper and compare it to the first paper. If the mark is bigger, you put it above because you want it in descending order. If the mark is smaller, you put it below. So after this step, you have two stacks of paper in descending order. Now a stack of two papers rather. And now you take the third paper and now you see where it fits with respect to the first two. Either it goes all the way to the bottom, or it goes between the two, or it goes all the way on top. Right? So in this way, at each point you pick up the topmost paper in the unsorted stack and you insert it into its correct position in the sorted stack that you are building up. Right? So let's see how this would work. So supposing we have our old array of unsorted elements. So what we do is we start with the very first element, namely 74. So we take 74 and we start a new stack. Now we have to take, now the topmost element at this point is now 32, the leftmost in this case. So now we have to take 32, and since it is smaller, it should go to the left of 74. Right? So we do this, so we now get this array. Now we look at the next element, namely 89, and once again it must go at the appropriate position with respect to these two, so it must go to the right of the 74, so we get this array. Now we take 55 and we have to find out where it goes, so we can start at the end and say it's not here, it must go to the left of this, and then we finally find that this is the correct place for it to go. Right? So this is the insertion step. We take each element and we walk down to the point where we want to insert it. Right? So 55 comes between 32 and 74. Now where does 21 go? Well, if we try to insert it, it turns out it must go all the way to the beginning because it's smaller than everything that we have so far. So this is the next step. And finally, when we do 64, it will come between 55 and 74. Right? So at each step, we pick up the next element and we insert it into the already sorted segment that we have created with all the previous elements. So we start by building a sorted sequence with one element. So this is called insertion sort. And we insert each unsorted element into the correct place in the already sorted sequence. So it's because of this insertion step, okay, that every element is inserted into its correct place, that this is called insertion sort. So this is a very straightforward iterative implementation again. So what we do is we have our initial array A, right, from position 0 to n minus 1. So what we do, of course, is at the beginning we have to do nothing. So we can assume that we actually start with position 1. So we start with position 1 and then we look backwards. So we start with the current position and we work backwards, and so long as the value that we are looking at, okay, is smaller than the value to its left, we keep moving. Right? So we have assumed that we have this swap operation which basically takes two positions in an array and exchanges them. Right? So swap A next pos minus 1 means take the value at A next pos, take the value at A next pos minus 1 and swap them. As we explained at the beginning, we can assume that such things are basic operations. It's convenient for us to express algorithms like it, as adding this only adds a constant factor to the number of overall operations that we have to do, which we can ignore in asymptotic complexity. So we swap each element with the element on its left so long as it is the element on the left is smaller, and we stop when we come to a position where the value on the left is greater than or equal to the current value. At this point we stop. Right? So this brings the value that we started with to the correct position. So in general, if we had say done up to some I, okay, and then I start walking backwards, then so long as I is bigger than so long as I is smaller than I minus 1, I will exchange. I will keep exchanging until I reach a position where I find that the values on the left are smaller than this value, and I will stop. So this is this basic loop, and I do this for all elements. So for each element I have to insert it. The first time I have to insert it in a smaller segment. As I go along, the segments we have to insert it in become longer and longer. Okay. So we can see now how this works on our array given to us. So we first of all start with looking at this segment. So this is my initial configuration. So this is sorted and this is unsorted. Okay. So now I will immediately see that 32 is bigger than 74, so I will exchange, and then because it reaches the beginning, so one of the conditions in that loop is that if I reach the beginning of the loop, so if next pos is equal to 0, I will also stop. So if I found it to the leftmost position, then this loop terminates, right? So having done that, then I have this. So now I must try to insert 89 into this, okay? So I will find that 89 is already bigger than 74, so nothing needs to be done. So the first non-trivial step that happens is with 55. So when I do 55, I compare it with 89. I find that 89 is bigger than 55, so I will exchange them, right? Now I will compare 55 with the element on its left, 74, and then again it is in the wrong way, so I will exchange them. And finally, having found that 55 is now bigger than 32, I will stop. Okay? So this is now the end of this phase. Now I will look at the next element to do, which is 21, right? So I will look at 21. So 21 will get exchanged with 89. Then 21 will be exchanged. So it will get exchanged all the way to the left. So I'll exchange 21 with 74. Then I will exchange 21 with 55. Then I will exchange 21 with 32. And now once again I will stop because I've reached the leftmost position. There's nothing to the left. Okay. And the last round I will take 64. Right. So now this part is all sorted. So I will take 64 and try to insert it here. So it will swap with 89. It will swap with 74 and then stop. Okay, so this is how insertion sort works. And this is a very intuitive sort. If you take a pack of cards and you try to sort it, typically this is how you would sort them. So if you look at the analysis, it is quite similar to selection sort that we saw before. Right? So inserting a value means you have to walk down that segment till the very end. Now, of course, one might argue that to find the position to insert, you can use binary search. Okay? You need not go one element at a time. If you want to actually find the position where it must go, you can use binary search. But even if you find the position where it must go in logarithmic time, you need to shift all the elements, and that is what really takes linear time. You need to actually make space for this. So in the worst case, you might have to put it in the leftmost position. So all the k elements which are already there must be shifted right by one, and that takes k steps. Okay, so binary search, although it can help us find the position faster, doesn't really help us to implement insert any faster. So insert takes linear time for a segment, and these segments keep growing. Initially, I want to insert A1 into a segment of size 1, then A2 into a segment of size 2, and so on. So I have 1 plus 2 plus 3 up to n minus 1. Finally, an minus 1 must be inserted in the segment A0 to an minus 2, which is of length n minus 1. Right? So again, I have T of n is 1 plus 2 up to n minus 1. And this is just a variation of this summation we have seen many times before. It's n into n minus 1 by 2. So this is again an order n squared search. So once again, as we saw for selection sort, there is a natural way to think of insertion sort as a recursive thing. We sort part of the array and then we insert an element into that to grow it, right? So in this case, we think of the array as being in two components, right? So we have a sorted portion and an unsorted portion, right? So what we do is we take the first element here and insert it, and then we recursively apply the algorithm to the rest of the unsorted portion. So if A0 to I minus 1, so if this is position I and this is position I minus 1, so I minus 1 is the last sorted position, I is the first unsorted position, then we insert AI into the sorted portion, and then we recursively sort AI plus 1 onwards. And once again, when I is actually here at n minus 1, then we don't have to do anything, so we can just trivially return. So now we have a recursive formulation in two parts. Okay, so we have insertion sort itself, which says sort this unsorted segment from start to n minus 1. Okay, so if start is already at n minus 1, return. Otherwise, insert the value at position start into the rest of A, which we will see below, and then recursively sort the rest of the array from start plus 1 onwards. So what does insert do? Well, it starts at the position start and tries to insert it into the segment 0 to start minus 1. So it walks backwards exactly as we had done it in the iterative thing. It finds the first position such that the value on the left is at least as small as the value we are currently looking for and stops there. Okay. So this insert is basically what was in the body of the iterative loop, but instead of doing an outer loop, we do it recursively. So how much time does this take? Once again, this is just to give you practice in looking at recursive algorithms and writing down the analysis. So whenever we have a recursive algorithm, we write a recurrence. That is, we write a formulation of t of n in terms of smaller values of t. So let's try to analyze this recursive algorithm. So we will analyze it looking at it slightly differently from the way we have formulated the algorithm. So if we want to sort a0 to an minus 1, then what we are doing is we are recursively sorting this segment and then inserting this value, right? So it takes time tn to sort the entire thing. This breaks up into taking time tn minus 1 to sort the first part up to n minus 2, right? And then n minus 1 steps to do the insert, right? So we get the same recurrence as we did for insertion, for selection sort. T of n is t of n, this is the insert phase, and plus t of n minus 1, which is the recursive phase, right? And if we expand this out exactly as we did before, we get n minus 1 plus n minus 2 down to n, which is n into n minus 1 by 2, which is order n squared. So again, there is no difference between the time for the recursive and iterative versions, except that one should keep in mind in general that recursive calls are more expensive than iterative loops. Okay, we will come back to this point a little later, but otherwise, if we count recursive calls, calling a function as a basic operation, then there is no difference between the recursive and the iterative versions. The recursive version is sometimes easier to conceptually understand and to code. So what we have seen is that the two natural algorithms that we would typically apply when we do something manually, selection sort and insertion sort, are both order n square. There is another algorithm which you may come across, which we will not discuss in this course, called bubble sort, which is not something that we would do naturally, but it seems to be a favorite way of describing how to do things on a computer. Okay, so bubble sort basically does this insertion kind of swapping, except it takes the maximum or the minimum value depending on which you want to do. Say it takes the maximum value and moves it to one end of the array. So then you have, like selection sort, the largest value at one end. Then you go back to the beginning, and again you keep looking at adjacent values and take the second largest value to the second last position, and so on, right? So bubble sort is also n square. But as we have seen, n square algorithms are not really feasible for large values of n. So if we have n above about 10,000, somewhere between 10 to the 4 and 10 to the 5, then n square is going to take several hundred seconds to execute, and therefore this is not going to be useful for large bodies of data. But this is not to say that these algorithms are all equally bad. In particular, it turns out that if you actually look at experimental evidence, then insertion sort usually behaves better than selection sort, and both of them are better than bubble sort. And to think about why insertion sort behaves well, just imagine what happens when we apply insertion sort to an already sorted list. Right? So whenever we want to insert something into the already sorted list, we will find that it's already in the correct position. So the bottleneck, which is the insert phase, is the bottleneck. The insert phase will basically terminate after one comparison. So insertion sort will essentially become linear time if we apply it to an already sorted list. So this is why in many situations, insertion sort actually behaves a little better than other order n square sorts. But in general, order n square sorting algorithms are not acceptable, and we would like to look at more clever ways of sorting data, because in order to sort large volumes of data, this is impractical.